Hello friends, welcome to this YouTube channel. Today we are going to solve a pair of numerical problems on three-phase induction motors. By solving these problems, we shall learn how to determine gross efficiency and develop torque of a three-phase induction motor for a particular value of slip using its per-phase approximate equivalent circuit when values of circuit parameters are given. A three-phase 3.3 kV 50 Hz 10-pole star-connected induction motor has a no-load magnetizing current of 45 ampere and a core loss of 35 kilowatts. The stator and referred rotor standstill leakage impedances are 0.2 plus J times 1.8 ohm and 0.45 plus J times 1.8 ohm per phase. Using approximate equivalent circuit, we have to determine rotor speed, stator current and power factor, develop torque and gross efficiency at a slip of 3%. Let us first write down the given data. Line to line terminal voltage VL equals to 3.3 kilovolt, that is equal to 3300 volts. For star connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 3300 divided by root 3, that gives us 1905.256 volt. Given stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.2 plus J times 1.8 ohm, and standstill rotor impedance per phase referred to stator side Z2S dash equals to R2 dash plus JX2S dash equals to 0.45 plus J times 1.8 ohm. For any value of slip S, expression for rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 3%, that is equal to 0.03 per unit. Therefore, Z2 dash equals to 0.45 by 0.03 plus J times 1.8 ohm. That gives us 15 plus J times 1.8 ohm. Let us now determine equivalent impedance per phase referred to stator side. ZQ equals to Z1 plus Z2 dash. Using values we get 15.2 plus J times 3.6 ohm. This may be written in polar form as 15.62 ohm at an angle 13.3245 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 1905.256 at an angle 0 degree divided by 15.62 at an angle 13.3245 degree. That gives us 121.9754 ampere at an angle minus 13.3245 degree. Given magnetizing component of no load current per phase Im equals to 45 ampere. Expression for core loss PC equals to root 3 times VL into IW. Therefore, working component of no load current per phase IW equals to PC divided by root 3 times VL. Given core loss PC equals to 35 kilowatts, that is equal to 35,000 watts. Therefore, IW equals to 35,000 divided by root 3 into 3300. That gives us 6.1234 ampere. Expression for no load current per phase I0 equals to IW minus J times IM. That is equal to 6.1234 minus J times 45 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 121.9754 ampere at an angle minus 13.3245 degree. This may be written in Cartesian form as 118.6919 minus J times 28.11 ampere. Applying Kirchhoff's current law at node P, we get stator current per phase I1 equals to I0 plus I2 dash. Using values we get 124.8153 minus J times 73.11 ampere. This may be written in polar form as 144.65 ampere at an angle minus 30.36 degree. Given slip S equals to 0.03 per unit, per phase rotor resistance referred to stator side R2 dash equals to 0.45 ohm. We have determined rotor current per phase referred to stator side I2 dash equals to 121.9754 ampere. For three-phase induction motor, total air gap power PG equals to 3 times I2 dash square into R2 dash by S. Using values we get 3 into 121.9754 square into 0.45 by 0.03, which is approximately equal to 6,69,510 watts or 669.51 kilowatt. Expression for total mechanical power developed PM equals to 1 minus S times PG. Using values we get 1 minus 0.03 into 6,69,510. That gives us 6,49,424.7 watt or 649.4247 kilowatt. Now we shall calculate stator copper loss. PS copper equals to 3 times I1 square into R1. Given per phase stator resistance R1 equals to 0.2 ohm. We have computed stator current per phase I1 equals to 144.65 ampere. Therefore, PS copper equals to 3 into 144.65 square into 0.2, which is approximately equal to 12,554 watts or 12.554 kilowatt. Since rotor core loss is negligibly small, stator core loss PSI equals to PC. Given core loss PC equals to 35 kilowatts. Therefore, PSI equals to 35 kilowatts. Now we shall calculate total stator losses. PS equals to PSI plus PS copper. Using values we get 35 plus 12.554, that is equal to 47.554 kilowatt. Let us now compute total input power. Pin equals to PG plus PS. Using values we get 669.51 plus 47.554. That gives us 717.064 kilowatt. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi1 equals to 144.65 ampere at an angle minus 30.36 degree. For star connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 30.36 degree, that is equal to 0.863. Lagging. We have computed total mechanical power developed. PM equals to 649.4247 kilowatt and total input power Pin equals to 717.064 kilowatt. Let us now determine gross efficiency of the motor. Eta G equals to PM divided by Pin. Using values we get 649.4247 divided by 717.064. That is equal to 0.9057 per unit or 90.57%. Given number of poles of the machine P equals to 10 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 10, that is equal to 600 revolutions per minute. Expression for rotor speed Nr equals to 1 minus S times Ns. Given slip S equals to 0.03 per unit. Therefore, Nr equals to 1 minus 0.03 into 600, that is equal to 582 revolutions per minute. Expression for developed torque Td equals to Pg divided by 2 pi into Ns by 6t. We have determined total air gap power Pg equals to 6,69,510 watts. Therefore, Td equals to 6,69,510 divided by 2 pi into 600 by 6t, which is approximately equal to 10,655.6 Newton meter. Now we shall calculate developed torque using alternative method. Td equals to Pm divided by 2 pi into Nr by 6t. We have computed total mechanical power developed. Pm equals to 6,49,424.7 watt. Therefore, Td equals to 6,49,424.7 divided by 2 pi into 582 by 6t, which is approximately equal to 10,655.6 Newton meter. A three-phase star-connected 400 volts 50 Hz 4-pole induction motor has the following per phase parameters referred to stator side. R1 equals to 0.15 ohm, R2 dash equals to 0.12 ohm, X1 equals to X2s dash equals to 0.45 ohm and Xm equals to 28.5 ohm. Fixed losses are 400 watts. Using approximate equivalent circuit, we have to calculate stator current and its power factor, develop torque and gross efficiency when the motor is operated at rated voltage and frequency with slip 4%. Let us first write down the given data. For stator winding resistance per phase, R1 equals to 0.15 ohm and leakage reactance per phase, X1 equals to 0.45 ohm. Expression for stator impedance per phase, Z1 equals to R1 plus JX1 equals to 0.15 plus J times 0.45 ohm. For rotor winding, given resistance per phase referred to stator side, R2 dash equals to 0.12 ohm and standstill leakage reactance per phase, X2s dash equals to 0.45 ohm. For any value of slip S, expression for rotor impedance per phase referred to stator side, Z2 dash equals to R2 dash by S plus JX2S dash, given slip S equals to 4%, that is equal to 0.04 per unit. Therefore, Z2 dash equals to 0.12 by 0.04 plus J times 0.45 ohm. That gives us 3 plus J times 0.45 ohm. Let us now determine equivalent impedance per phase referred to stator side. ZEQ equals to Z1 plus Z2 dash. Using values we get 3.15 plus J times 0.9 ohm. This may be written in polar form as 3.276 ohm at an angle 15.9454 degree. Given line-to-line terminal voltage VL equals to 400 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.94 volt. Expression for fixed losses PC equals to root 3 times VL into IW. Therefore, working component of no load current per phase IW equals to PC divided by root 3 times VL. Given fixed losses PC equals to 400 watts. Therefore, IW equals to 400 divided by root 3 into 400, that is equal to 0.57735 ampere. Expression for magnetizing component of no load current per phase IM equals to ET divided by XM. Given magnetizing reactance per phase XM equals to 28.5 ohm. Therefore, IM equals to 230.94 divided by 28.5, that is equal to 8.1 ampere. No load current per phase I0 equals to IW minus J times IM, that is equal to 0.57735 minus J times 8.1 ampere. We have obtained equivalent impedance per phase referred to stator side ZEQ equals to 3.276 ohm at an angle 15.9454 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 230.94 at an angle 0 degree divided by 3.276 at an angle 15.9454 degree. That gives us 70.4945 ampere at an angle minus 15.9454 degree. This may be written in Cartesian form as 67.78215 minus J times 19.3663 ampere. We have computed no load current per phase I0 equals to 0.57735 minus J times 8.1 ampere. Applying Kirchhoff's current law at node P, we get stator current per phase I1 equals to I0 plus I2 dash. Using values, we get 68.3595 minus J times 27.4695 ampere. This may be written in polar form as 73.6722 ampere at an angle minus 21.8922 degree. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi1 equals to 73.6722 ampere at an angle minus 21.8922 degree. For star-connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 21.8922 degree, that is equal to 0.928 lagging. For three-phase induction motor, total input power Pin equals to √3 times VL into I1 cos phi 1. Using values, we get √3 into 400 into 73.6722 into 0.928. That gives us 47,366.602 watt. Expression for total air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to stator side R2 dash equals to 0.12 ohm and slip S equals to 0.04 per unit. We have determined rotor current per phase referred to stator side I2 dash equals to 70.4945 ampere. Therefore, Pg equals to 3 into 70.4945 square into 0.12 by 0.04. That gives us 44,725.271 watt. Expression for total mechanical power developed Pm equals to 1 minus S times Pg. Using values, we get 1 minus 0.04 into 44,725.271. That gives us 42,936.26 watt. Given number of poles of the machine P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values, we get 120 into 50 divided by 4, that is equal to 1500 revolutions per minute. Now we shall determine gross efficiency of the motor. Eta G equals to Pm divided by P in. We have obtained total mechanical power developed. Pm equals to 42,936.26 watt and total input power Pin equals to 47,366.602 watt. Therefore, eta G equals to 42,936.26 divided by 47,366.602. That gives us 0.9065 per unit or 90.65%. Expression for developed torque Td equals to Pg divided by 2 pi into Ns by 6T. We have determined total air gap power Pg equals to 44,725.271 watt. Therefore, Td equals to 44,725.271 divided by 2 pi into 1500 by 6T, which is approximately equal to 284.73 Newton meter. So today we have solved a pair of numerical problems on three-phase induction motors. By solving these problems, we have learned how to determine gross efficiency and develop torque of a three-phase induction motor for a particular value of slip using its per-phase approximate equivalent circuit when values of circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.